So to find the equivalent for forces, that is, sum of the forces is equal to mass acceleration, we need something equivalent for rotation. We already know that our equivalent for mass is the moment of inertia I, which is in the form of mr squared, at least units. The equivalent for acceleration is angular acceleration, which is equal to acceleration over r. So if we put those sort of in terms of units, notice that we've got an m, an a, and an r. So our equivalent here needs to have the units associated with ma, force, newtons, times a distance, a newton meter. And so this needs to be a force times r. And so that's our driving idea here, that for our the equivalent case, Newton's second law for rotational motion turns out to be the sum of the torques times I alpha, where our torque is given by the radius times r. The magnitude of the torque is equal to r times the force times the sine of the angle between them. So for example, let's say we've got a bicycle wheel that's mounted right here. So a stationary bike, something like that, is mounted like this. We pull on it like that. There's our force. Our R always goes from the point of rotation out to the point where we're applying the force, for example, or any point we're interested in. But when we want to find the torque, it's to wherever the force is applied. So this is R. So if I redraw them over here, R is like this, and our force is like this, and the angle between them in this case, this phi is equal to 90 degrees. And so in this case, the torque is just R times F, which has the right units as we've argued up from above. Now the reason for saying sine of the angle between them is that we can apply forces in a way that is not particularly useful. So if, for example, we look at this wheel, we apply our force again at this edge, but we apply it like this, I think you can see that the only, there's my R again, that the only part of the force that works towards rotation is this component right here. We want this component of the force. Right? Because the part of the force that pulls in this direction is just working to pull it across the room or pull it off of its axle, if this is where the axle is, right? As it has to be for this to rotate. And so the component of the force that we care about is this Fy. So really the torque, what makes sense to contribute towards rotation is R Fy in this case. And if we redraw this, again, redraw, here's our R, here's our force, in this case, there's our force, here's our angle, phi, then if we look, we can recognize, hey, this Fy, we can say sine of phi is Fy over the magnitude of the force, or Fy is equal to F sine of the angle between them, which is just what we have up here. Now that's the magnitude of the torque. This should look familiar. This should look like something we've already defined before. And that is that we could say our torque is equal to R cross F, because the magnitude of our cross product is just R times F times the sine of the angle between them. Now the direction gets a little trickier, but you can handle this. If we've got a force going in the direction that we're going, and we were starting from rest, then I think you could agree, in either case, that our omega would be this direction, because that would be the way it would rotate around. I mean, that's not really the direction of omega. That's the direction this is going. We'll figure out the direction of omega in a minute. But then alpha, because the force is happening, alpha and omega must be in the same direction. And so to find the direction of omega with a circle, then if we've got something that's going around like this is the direction it's going around, then to use our curling right-hand rule, so if you look at it at the screen, what I think you get is an omega that's into your computer screen, Check that you see this as you're watching this video, right? Put your hand up at the screen and make sure that your thumb, right? Thumb points into the computer screen with the curling right-hand rule. So you take your fingers like you're sending this around in a circle, and your thumb points into the computer screen. So alpha and omega are all into the computer screen. Let's check if our R cross F gives you the same thing. So doing here's our R and our F down this way using the cross product right-hand rule. Okay, then that means on our right hand, R is on our first finger, pointer finger. F goes along the middle or the second finger. And the answer, the torque, the direction of the torque, will be along the thumb. So again, if you take your right hand, get it up near the screen, you get your first finger like that, your second finger sort of down along F, then I think you'll find that your thumb, again, points into the computer screen. So here we have the torque is pointing into the computer screen, and up here we see that omega and alpha, because it's speeding up, are both into the computer screen. So they point in the same direction. So what that says is that defining the torque as R cross F works so that we have the torque is equal to I alpha. It makes sense in terms of the cross product works in terms of the right amount of force providing the speeding up. The units work. The units of torque are Newton meter, and the direction works because the torque is in the same direction as the angular acceleration. Finally, we can connect to work and power as well. We know that work is force times displacement as long as the directions are correct. So force times displacement times the cosine of the angle between them in one dimension with a constant force. Similarly, for situations where we have a constant torque, and that's the only kind we're going to deal with, constant torque, we're going to have then our work, instead of force times distance, turns out to be torque times the angle we go through. And that's going to have the same units. If we think about this, this makes sense because torque, the distance, the theta is S over R, and T divided by R would just be a force times S, where this is a distance or a displacement that we've gone through. Same as over here. So if things are lined up nicely, then, with a constant torque, then we can just find the torque that's applied. We've already taken into account the angles by saying what part of the force is actually doing any work with the torque. And so we're just left with this. Then if we go to power, which is change in work with respect to time, then over here, that becomes derivative with respect to time of torque times theta, but this is already for a constant torque, so torque is d theta dt, so this is torque times omega. And so this is our value for the power.